Part of my talk, well, not part of my talk, easily 60% more of my talk was reshaped after a considerable amount of feedback from some of the people here. And particularly, I also want to thank some of the grad students that helped me to reshape my talk so that it could be reachable. I know that sometimes the geochemistry is a bit of a challenge. There are no uncertainties in what I'll be talking about. I'm really very happy having Steve Dye here. I've been paying attention to uncertainties, and I thought I was doing a very good job, but Steve Dye in the back of the room is a particle physicist, and I've been working with Steve and others in the physics community on a project of geoneutrinos for the since 2004, 2005. And I remember I went to my first particle physics meeting, and I was impressed by these guys. I had already started reviewing papers, and they've been quoting all of our literature. Prem was quoted, my composition of the Earth was quoted, and all this other stuff. And I was going, wow, these people are right on top of it. So I'm at this meeting in Hawaii, and it's my first one, and I'm a bit intimidated. And the first coffee break appears, and Mark Chen comes over to me. So he's now the head of the Snow Lab experiment on geoneutrinos. And he holds up a copy of Nature 1984, Joachim et al., which is Joachim, Hoffman, and a few other people. And it's the fundamental statement we were using for a long time on the potassium-uranium ratio. And those of you who might know this, it comes out with the statement that the potassium-uranium ratio of the silicate Earth is 12,450 plus or minus 250. And the first question this fellow said to me, "You're familiar with this paper?" "Yes." "How certain are you about this uncertainty?" And I immediately said, but the implication is that there is an entirely different discipline, be it as in the case of Dave and Sarah, the astronomers looking at our work, or be it in the case of Steve Dye, the particle physicists looking at our work. And really, I've been pushed in many, many ways by the particle physics community to treat uncertainties. And in fact, I've pushed back, too, because they want to know what is the uncertainty on the silica content of the silicate Earth. So just SI. Well, in 1995, I came out with a paper, and Jeff Davies was one who pushed me on uncertainties. And Jeff Davies said, don't just publish your composition, but put an uncertainty. So in my 1995 paper, the one column that has an estimate of the uncertainties was pushed on to me by Jeff Davies, insisting that he needed to understand how confident a geochemist is about this estimate. So for my minimum uncertainty, I said plus or minus 10%. So that would be calcium, that would be magnesium, that would be iron, and that would be silica. Immediately after publishing my paper, I mean within weeks, I said the silica content is 44.8 plus or minus 10%, and that would have a perspective on the magnesium-silica ratio and a perspective on what the upper mantle composition would be, as well as the lower mantle. I got a letter from Don Anderson saying, I really like your paper, I really like your composition, and there's no difference between your composition and my composition. And believe me, there's a world of difference. But within uncertainties, I will begin by saying that Murakami et al. Paper that we were just talking about, the lower mantle, and say McDonough and Son, more pyrolytic type mantle, we can't tell the difference between them. I'll be very strong. I am not giving up my model. I don't think the Murakami position of a perovskititic lower mantle with almost free of ferropericlase. I don't think that's tenable. I just don't think that model's tenable. But first statement is, within uncertainties, almost everything I say is acceptable, as well as other models. Only for a brief reason, I just want to correct, what do we mean by the mean age of the Earth? To a geochemist, often, and it was talked about earlier, oftentimes, well, the formation of the Earth. Since there is no birth canal, you know, the whole thing is what do you say is the day that the Earth was born, right? I mean, and, you know, we're losing mass and energy from the Earth today, and we're also gaining by the rain droplets of comets that fall every day, every night, all over the entire sphere. Okay, so at some point we've gotten to a point where with negligible growth, the functional mass of the Earth was probably made within the first 10 to the 8th years. But when we talk as a geochemist, most of our isotope stories really get to a resolving power that's about 2/3 of mass, or something like that. So the mean age is often the value that we're talking about, and the mean mass is around 2/3 or something like that. Okay? So keep that in mind when somebody says the age of formation. You have to constantly ask yourself, from what perspective are they talking about, quote, formed? Okay. We could talk about core formation, but even if you look at some of these simulations, you did form a core, and then you formed more of it. So it's a very dangerous word about when you say the age of the Earth. Okay. Classification of elements and classification of meteorites. I will go into this because of the good guidance I received. There's a couple of slides at the end that I don't plan on talking about. One is a true taxonomic classification tree of meteorites, and the other is really some of the hoary details about certain chondrites. And we don't have to go over them, but I added them in the spirit of what Sarah did, additional context of information. They are part of the information set that you can have. In addition to the video, I assume the PowerPoint slide sets are being made available, right? Okay. So that's that particular information. And what do we mean by chondrite? Okay. This is fundamental. This is really fundamental. When Rick Carlson says about the samarium-neodymium ratio of chondrite is X, X has a very small plus or minus Y. There's very small differences. Samarium, neodymium, all the rare earths, calcium, aluminum, these are refractory elements. In our models, when we say it has a calcium-aluminum ratio of 1, we're talking about order on the ratio uncertainties of 10% when we say a samarium-neodymium ratio of 0.196 or some number like that. We really mean it to that many significant figures with this very small difference. Here's the next important point for all seismologists and all mineral physicists. There is no such thing. There is no such thing. There is no such thing as a chondritic magnesium-silica ratio. I've been in the business for easily 30 years, and I can't tell you how many papers I've read and how many times I've heard it at meetings. I used a chondritic magnesium-silica ratio. So you get the knee-jerk reaction, which one? Okay? That's a very important issue because when you're talking about mineral physics, you're talking about a perovskitic lower mantle versus an olivine mantle. So the word chondrite is exceptionally useful, but just horribly misapplied all the time. So there's my Homer Simpson. All right, I'll just okay, there are several competing compositional models for the Earth. That's got to be an understood statement. And that means if they're competing, they're in the game. Okay, they're in the game. Someone must be right, and I was already accused, you can't say that. And I said, well, that's why I added the question mark there. So I said it there. And I know it irritates some people to say somebody must be right, and then I get nervous. But we all can be partially right, or we could all be wrong. And believe me, I will mention occasionally the word geoneutrinos, because I now give no talk without saying that word. But there's hope for the future in that the particle physics community is actually going to provide us some insights on the abundance of elements inside the Earth as they exist today. Why is that important? Because the difference between geophysicist and geochemist is that a geophysicist is looking at the instantaneous Earth, and a geochemist is looking at the time-integrated Earth. We are fundamentally looking at two different beasts, as Barbara showed in her first picture of the elephant with many different parts. And a geoneutrino measurement will measure the composition of the Earth as it exists right now. Okay, so that's what's really cool. It's the first measurement of the instantaneous Earth, and it will constrain us with time. All right. We really do not know the composition of... Pardon me?
Are you going to explain that statement?
Barbara, he wants me to give another talk. Oh! I've actually already given a geoneutrino talk here, and but
That's a very strong statement, unlike the other one.
yeah, I cannot go off on that tangent, but the products from the decay of uranium and thorium can now be measured in detectors inside the Earth that you build and put inside the Earth. We really don't know the composition of the lower mantle, and that's, for me, in this story, that's the big one. That's the big one. We know the composition of the upper mantle pretty well, in fact. That's because we get lots of samples. And every time, if you've ever had a chance to read the paper I wrote on the composition of the Earth, it came out, and I felt really strong at one point in time. It came out just when we were getting all these tomographic images of slabs going down, and I felt, now I can do a really strong argument that there is whole mantle convection, or at least a mass transfer between the upper and lower portions of the Earth. And I felt more comfortable about saying that the upper mantle and lower mantle are not grossly different in composition. If you tell me that there is limited or almost no mass transfer between the large portions of the lower mantle and the upper mantle, then we're in trouble. I, as a geochemist who measures samples plus studied meteorites, am restricted to telling you stories about the samples I have. So I remember 25, 30 years ago when Raymond Jeanlot and Elise Niddle were talking about core mantle exchange in some of their experiments. I remember we had this discussion, and I was saying, I see zero zip, not evidence for mass chemical exchange between the core and the mantle in the last 3.5 billion years. But if what you're talking about is happening down there and we don't get a sample, I can't tell you about it. Okay? So from a geochemist's point of view, we often talk about what we can measure. All right? So that's an important issue. If we don't touch it, we really can only speculate just like the rest of us. So there may or may not be hidden reservoirs in the mantle is the next thing, and that's important because I'd say you have to push us up against the wall when we start invoking things called hidden reservoirs. But we do it for very, very valid reasons. It's not just an ad hoc reason. And some of these reservoirs are readily explained and some of these are not. Sometimes the hidden reservoir for some people become the Earth's core because that's even more remote. Okay, but there may be domains in the silicate fraction of the Earth that contain material that were taken out of the equation very early on and held down in a basal magma ocean, and we have to see if there's a missing component, and that's how it drives us to that concept of hidden reservoirs. And this is another extremely important takeaway message, and I'll drive it home in about 5 to 8 slides. We have a very incomplete meteoritic record. Okay, try and keep that in mind. There's less than 10,000 meteorites in our collection, and only really 1,100 of them are falls, so therefore they've not been messed around with too much by surface processes. Steve.
So let's see, the third and fourth statements, right? So, when you're doing the box models and a mass balance, you can only get, n-1, you can only get know the composition of a hidden reservoir if we know the composition of all the other reservoirs in the bulk Earth. But given that you say we don't know the composition of the lower mantle, isn't that the one that, if you have that in your box model, then you can't determine the composition of a hidden reservoir because then you've got two unknowns.
Good point. All right, so you and I and many other people in the room will agree we often have at an absolute minimum, 3 unknowns. We've got the continental crust, we have this depleted mantle, what we frequently refer to as the source of mid-ocean ridge basalts. And for an abundance of reasons, we know that there's another reservoir in the mantle which gives you Hawaii and various other things, often called hotspot magmas, plumes, or intraplate magmas, which is a very good word. So that's 3 reservoirs, and the starting composition would be the primitive. So you already know that we have that many unknowns, more likely is the better statement. So we can get an infinite number the potential goes to a large number of solutions, right? And then we invoke a hidden mystical reservoir. How do we do that hidden mystical reservoir? Because we, like you, as in seismology, you need a reference frame. Our reference frame is chondrites, and there are some ratios, such as the calcium, and I will talk about this a little later, the refractory elements become a given rule space for building models. And I actually go through that a little bit later on. So that's actually where we get that constraint. It can't be a volatile element like potassium in the Earth. It has to be amongst the refractory family of elements that give us hard ratio constraints. And for instance, say we're missing an amount of calcium. You aren't permitted to put it in the Earth's core, okay? And I guarantee you're looking at me going, you can't put calcium in the Earth's core. And I just say you're just lacking in intelligence. Give time. Petrologists can put anything into anything. I mean, if you need to be reminded, Ramamurthy had a really wonderful, provocative paper about potassium in the Earth's core because he was able to experimentally show that potassium will go into a sulfide phase, which will go into the Earth's core. He didn't really emphasize too strongly that his bulk composition was 30 weight % potassium, and the Earth doesn't have 30 weight % potassium. So be flexible. Calcium can go into the core. What?
Are you saying that petrologists in general...
They're like geophysicists. What would you like it to be? Oh, I also have another expression, which is the periodic table is not a one-stop shopping place. If you buy some potassium, you just bought some sodium, lithium, rubidium, and cesium. You know, the columns are important.
It's a bundled purchase.
Yes, it's a bundled purchase. That was my beginning slide. And we don't know these time scales. But I will tell you, Dave Stevens and I, at some level, grew up with Ted Ringwood around us, right, early on. And the thing I remember, Ted was a big fan of the Safronoff model, but he was paying attention to the Weatherall model for building of planetary systems. But the thing that, you know, you're going to quibble in detail, maybe factor of 2, maybe 20, maybe 40 million years down here. When I was growing up, that was 10 to the 8th years always. This was 100 million years, 200 million years. Okay, so I did my PhDs in the 80s, and in the 80s, those numbers were 10 to the 8th. Those numbers were guaranteed 10 to the 8th. So we've evolved a lot in that period of time. When building an Earth, and we've heard a lot about all the other things, I will go back and forth between Earth and planets. When building Earth, building planets, we often refer to the chondrites as the building blocks of planets, or something, the starting material. Okay, so when we're talking about the solar nebula, let us not forget there's one piece of information that's fundamental, and you learned it in grade school. There's the rocks and the gases. That tells you, to me, chemically, I don't care how it got there because you could have loved the Grand Tack model or not, chemically, the solar system is fractionated. Okay, that's an important thing. The distribution of volatile elements, and I will give you a definition of volatile elements, but those you can easily, half the periodic table, okay? Half the periodic table is volatile elements. The volatile element distribution in the solar system is grossly fractionated. That's the first thing. Okay, there are gradients and heterogeneities. Sorting, size, CAI, that's a calcium aluminum inclusion. Rick Carlson talked about it. These are the oldest precipitated mineral phases in the solar system. This is how we actually define the age of the solar system. It's like trying to say, what's the age of the Earth? Well, age of the solar system is kind of a wacky thing too. There used to be an interstellar gas dust cloud. Some large explosion in space happened, gave momentum and mass, some of the short-lived radionuclides. It then goes in that previous picture, and we accrete. Well, the really, quote, beginning of the solar system is only defined by the presence of calcium aluminum inclusions. But, very shortly after, as Rick was talking about, we formed chondrules, these little melt droplets. And then matrix, well, that's the remaining dust material, if you will. And this, and this end up making a chondrite. And chondrites should often be thought of like at the bottom of river valleys before it hits the plain. There are a lot of different rocks at the bottom of all river valleys. And so you go there, and there's the river, and there may be a dry valley like you have around here. every rock uphill, plus some of the rocks just near the bottom of the hill, plus the mud. Okay, that's some of these chondrites. But what's really interesting is some chondrites, like the enstatite chondrites, only have a very restricted range of oxygen isotopes, and ordinary another restricted range. So although they're a heterogeneous mixture, maybe a multilithologic assemblage, there are certain discrete characteristics about them. All right, so there is sorting of size and density and crystallinity. I'll show you briefly that there's even a change in crystallinity with time as the system is evolving in the nebula. And big important thing is redox conditions. And the redox condition, that just means how much rust is available. How much did you have iron locked up as steel, and how much of the iron was locked up as red hematite, iron oxide, if you will. And there are two environments, something that happened in the nebula and something that happened on what we call a parent body. And a parent body would be like the Earth or the asteroid belt or other things. So compositional models differ widely, implying a factor of 3 difference in calcium, aluminum, uranium, and thorium content of the Earth. So there are just about 40 elements which we call refractory. I'll show you that in a couple of slides. But if I know the uranium content of the Earth, I know the calcium content of the Earth. If I know the thorium content of the Earth, I know the aluminum content of the Earth. Why is that? Because the chondrites have conserved ratios in the refractory elements. Silica and magnesium are not refractory, so they're anybody's guess. Okay.
So the assumption is if the Earth is chondritic, then if we know one, we know the other.
Right, and I'll go through that in a second as to why that assumption looks good. All right, so read the sentence. Okay. Earth models update. Just in the last 9 months, you're going to get this just in the last Murakami et al., May 2012. The lower mantle is enriched in silicon consistent with the C1 chondritic Earth model. Said in Nature. I love these journals. I got to publish in these more frequently. Campbell and O'Neill, March, same journal. Thank you for the update. This means that the internet is back on, I guess. My Dropbox has been filled. The same journal, 2 months later, there's evidence against the chondritic Earth, right? Okay, we must actually understand the system. It's your reference frame. March, same month. Different journal, I don't know about this journal. The titanium composition of the Earth and Moon overlap with that of enstatite chondrites, right, Dave? We know what we're talking about. Don't you worry. Fitoussi and Bourdon says silicon isotopes support the conclusion that the Earth was not built solely from enstatite chondrites. It's coming clear now. Paul Warren. I've stooped to a lesser journal, right, Mark? Among the known chondrites, EH yields a relatively close fit to the stable isotopic composition of the Earth. Yeah, so what is it? Should we take a vote? We don't know. All right, so...
The last one is a much different statement.
It is. Yeah, it is. But the problem will be, I don't pay attention to chondrites, but don't require things of them, okay? They are guides, simply guides. All right, so here's a little history. A lot of words on this, but go away. I don't know how to turn that off, by the way.
Let's go.
All right. Ask away, whoever it is.
Go back, previous slide.
No, I'll get... EH. Yes, it's all in when you introduce something. And you probably, there's so many things to simultaneously introduce. Please continue to do that. That's a good question. EH. Rick Carlson talked about it earlier in the week. E stands for enstatite. H stands for high iron versus L, low iron, versus ordinary chondrites are LL chondrites, low iron. Yeah. You know how geochemists can't do calculations? Well, we only think of very simple words, high and low. So that's what EH stands for. It's an enstatite chondrite. And I have a few slides to give you some clarity. I hate to use that word. Understanding as to how meteoriticists classified these meteorites. And that's a couple slides. Yes, Ed?
So a non-specialist, me, I could look at this and
that some things are more sensitive to being a probe of our chondritic or not starting nature versus it's like, okay, maybe the first Murakami statement that, well, silicon doesn't distinguish because it's just chondritic. Maybe.
Well, let me point it out. See this word titanium isotopes? Think PKIKP. See this word silicon isotopes? Think SCS. Yeah, I think that would be. In fact, I'm positive that silicon isotopes is an SCS reflector. Yeah, it's bad, isn't it? Gets very confusing, but yeah, you're right. There are some things you can make strong statements on, and some things you can't make strong statements on. And you know, like in the oh, you want me to editorialize something that's been published, right? Well, you know, actually the Murakami study was really interesting. Let's see, what is it? The lower mantle is enriched, consistent with. There's the use of consistent with. But it's a really bold statement, as long as it doesn't have aluminum in its composition, because our experiment couldn't put in aluminum. Technically, you need to know those details. So as it is in seismology, as it is in geochemistry, as it is in mineral physics, as it is, we try to talk to everybody. I didn't tell you about all the details, you know? And I particularly will not tell you about some of the blemishes in our arguments. I'll only tell you about the bright spots in our argument. Now, nobody's trying to actually, you know, some of us are just trying to get a paper in Nature, which is always fun to do, won't disagree. But it's the reality of today. Well, Paul Warren, I'd call him a petrologist, but you could call him a geochemist also. Yeah, these two are isotopes. Yeah. Yeah, chondritic is at least still part of the equation that people agree to use in the story. Now, the reason I go back and forth, and you'll see as often I'll talk about thorium uranium, because that will actually be weaved through the talk. Oh, it will just take too much. The reason I constantly talk about these two elements is, one, it's a focus of the work I'm doing with geoneutrinos, but two, as I said a few slides back, if I know the calcium content of the silicate earth, I know the uranium content of the silicate earth. Now, the calcium content is running around 3 weight % calcium, and the uranium content is running around 20 parts per billion, if you take my model. And today's talk, I'm going to just talk about how the models are built. I'll be talking on Monday, and I'll be talking about some of the differences in the way these different models were built. But to get through today's talk, I'll frequently go back to, of course, the correct or the right model, which is called McDonough and Son. But in that perspective, the usefulness is that, let me just say, most recently, if you got something like Turcotte and Schubert, you're up around 30 parts per billion. And there's mine at 20. Geochemist, ready for geochemistry? Hart and Zindler, 20. McDonough and Son, 20. Allegre, 20. Palmy and O'Neill, 20. I mean, you know, it's we all use the same formulas, the same rationale. So we keep coming out at 20, plus or minus some number. Okay. But, you know, later O'Neill and Palmy went to 10. And then one I will frequently refer to, Marc Javois, he's down at around 12 parts per billion. That's in grams per gram times 10 to the minus 9 for those. This is a family of what I will call cosmochemical arguments. This is a family of geochemical arguments. And this is one, not all, a family of parameterized convection or geodynamic models. Okay? But that's the range. So from the perspective of, say, a model that I like, there's a factor of 2 lower and, you know, well, from the other one, a factor of 3 total range. Okay, I'll go through that. The question was, how did Wasserberg? So this is actually a point of view that's been evolving, but not evolving in markedly broad, different reaching areas. We go back to we go back to the original articles talking about how elements are made in stars. We actually have some nucleosynthesis models that give us constraints on what might be the production of uranium relative to silicon or thorium relative to silicon during stellar sequences. You know, when supernovas occur, that's when we build elements greater than iron. Okay, and in fact, people have looked at what is the mean uranium-thorium concentration in the galaxy. And, you know, in fact, they've even gone as far as to estimate the age of the galaxy based upon the ratio of thorium to uranium. Okay? And that would be as a result of production and decay. So we actually have a constraint that comes strictly from the astronomers and the physicists. Okay? So that's one thing to keep in mind. And Harold Urey knew this in '56. And, in fact, Harold Urey wrote this great paper. It's about 4 pages long. It's really worth reading. In the old PNAS in 1956. And he used this argument, and this argument, which is chondrites, to really begin the first story. He actually concluded, he said the bulk Earth had 11 parts per billion uranium. And then, of course, if you don't put any uranium in the core, that means there's 16 parts per billion uranium in the silicate Earth. But this argument, which was basically the first paper that he wrote, was the potassium, thorium, and uranium content of the Earth, Moon, and Mars, and heat production on these planets. It was all done. It was really a fantastic paper. And what the range is going between 30 and 10, and he's right in the midsection. We didn't have great data on meteorites back then. And back then, we just called them chondrites. We didn't divide them into chocolate, vanilla, and strawberry. They were just chondrites back then. Life was easier. Okay? And he just took the average of what we knew for chondrites at that time. But heat flow becomes an important issue because you put your hand in this blue sphere, turn the light off, right? Put your hand on the blue sphere and you say, how warm is the Earth? Okay? So it's exuding, as you'll see later in the talk, about 46 terawatts. And then you have the whole confusion as to, well, what does that exactly mean in terms of the initial, what we might call primordial heat relative to how much is being produced today from radioactive decay. So that's what heat flow is really a big issue about. It's trying to actually deconvolve those two stories. Modeling composition, that's today. We're really, really gnashing our teeth as to which chondrite we should use, and that's what this talk is about today. Wasserberg, to get directly at that question of Wasserberg had a phenomenally great paper in 1963. This is a science paper, and what he had used there was to try. This is the time when we're just getting on to samples of the ocean floor. Paul Gast has measured the strontium and rubidium content of ocean floor basalts. There's been a bunch of measurements made of the strontium content of the continents. We know that the continent ratio of 87-86 is about 0.71. Who cares about a third significant figure? And then they go into the ocean, get a piece of the Earth's ocean floor. Remember, this is history. This is only in the 60s when we're really getting this information. They measured the strontium isotopic composition of an ocean floor basalt, and it's 0.7. Well, all I need to use is one significant figure. Why? Because chondrites are 0.8. Okay? In terms of the 87-86 ratio, the two reservoirs we knew, the ocean floor and the continents and every magma erupting in Hawaii, everything we kept touching and tasting was 0.7, not 0.8. Okay? And we're getting ready to go to the moon. What will the moon ratio be? It told us without question every sample we had available was depleted over the time of the history of the Earth in rubidium. Okay? Because rubidium-87 decays to strontium-87, and your 87-86 strontium-strontium ratio tells you how much rubidium you had in your past. Okay? So we knew that the Earth must be volatile depleted. Okay? Shortly after that, at the same time, Wasserberg says, all right, let's see if it's lost potassium. And that's another volatile element, and you might predict it to be as volatile depleted as rubidium. So what you can do, you can measure the potassium-uranium ratio, because we find that the geochemical behavior of uranium is just like the geochemical behavior of potassium. So we measured a whole bunch of rocks from the continents, really easy to get your hands on. Potassium-uranium ratio varied, but it was essentially 10 to the 4. It was 10,000. Maybe you had some that went to 20,000. Maybe you had some that went to 5,000. But let's not get too fussy. It was 10 to the 4. We go to the ocean floor and get some very fresh pieces of glass. What did they find? The ratio was 10 to the 4. And they said, well, the crust in the, quote, mantle, and the mantle was being represented by lavas coming out of the mantle, like as in the mid-ocean ridge, were approximately 10 to the 4. So that's when we first estimated the potassium content. And then, well, potassium-40 decays to argon-40. We have argon in the atmosphere, and it's not just atoms of argon, but it's actually the argon-40-36 ratio is 300, but chondrites, basically all the 40 that's in the atmosphere is all due to decay of 40. That's what the argument is. So that tells us that we had at least 120 parts per million potassium inside the silicate fraction of the Earth, because we have that much atmosphere of argon. 1%, by the way. As we breathe and listen to me go on and on and on, you're bringing in about 1% of argon and you're not interacting with it at all during your breath. But he then looked at the argon argument, then he looked at the helium argument, the helium 3-4 ratio, and he looked at the heat flow, and he ended up actually estimated, he estimated that the bulk silicate Earth, if I remember this correctly, had a uranium content around 33. And these are some very, very early on powerful arguments, and we've only actually been adding details to that ever since. This is a purely cosmochemical argument, 18. Ted, look at that. Ted is at 20 ppm, and then we're also at 20. That's the origin of our model. This is the pyrolite model, and it says I look at basalt, I look at pearitites, I look and I go, yeah, 20 ppm, okay, 20 ppbs. So that's where this comes from. Yagut says I want to reproduce his model. Schubert et al., Davies et al., that's parameterized convection, and that's really how to keep it stirred and not overheat. So it's really a balance between the viscous forces and the heat dissipation rate. Okay, so that's a fine argument, and some people go, yeah, but you got to think about that. It doesn't matter. It's a model, and we're going to test it. And it irritates me all the time because this book is like, Sarah and I go, that's where we go for all our information about how geodynamics works. So you read that book, and that since the 1982 version of the publication, they'll tell you the amount of uranium in the Earth is 31, the amount of thorium in the Earth is 4 times that number, and the amount of potassium in the Earth is 10 to the 4 times that number. It's the Bible in many ways. So, no. I'll skip that one. And O'Neill and Palme, you go, how do you go from 20 to 10? Anybody know? No, Matt, don't say it. What? Yeah. Yeah, he said, I want to be first author. No, I want to be first author. Yeah. Yes, at some level. What he did was he built this Earth, and then with a baseball bat, he whacked off a whole bunch of crust that was at the top. It had a lot of incompatible elements and made Rick Carlson very happy because it satisfied the 142. But Rick Carlson says, no, you're wrong. Because Rick has a fraction of the Earth in a hidden reservoir at the base, which he would refer to as his early enriched reservoir. And it brings clarity to the neodymium 142 argument. So if you get anything from this talk, pay attention to the neodymium 142 argument, because it will drive some of our models. And that would be the difference. I would guess that Rick Carlson is comfortable with approximately 20 parts per billion uranium in the whole Earth. But some of it is stored down at the bottom and is acting as a hot plate to convection. Okay? That's just one way to think about it. Whereas these folks think that collisional erosion have the uranium abundance. Okay, so that's what that's all about. All right, so now I'll step back and repeat it because it's a very important message. If you know the uranium content of the Earth, you have some strong idea about the calcium content of the Earth. I'll talk about Javois' model. It's a purely cosmochemical model, and it is purely amongst the cosmochemical family of models. It's an Enstatite model. It really says, I know the flavor of chondrite that formed the Earth. All right, and I've emphasized this, so I'll be very quick. Radiogenic heating versus secular cooling. It's really talking about the abundance of elements in the potassium, thorium, uranium scheme. The estimated bulk silicate Earth varies from 9 terawatts to 36 terawatts in all those models, by the way. It gives us definitely clues to planet formation. The amount of radiogenic power in the mantle. This is very specific to the mantle. Now, Mark Harrison has absolutely been playing a brilliant role here because he keeps saying, We don't understand the continental crust. He doesn't live with Roberta, so that's why he doesn't understand it. No, to understand the continental crust is truly far more important than, for me, far more important than understanding the silicate Earth. Really, we really have to do a better job at understanding the continental crust. There's no question in my mind. Now, if you think the continental crust is described either by Rudnick and Gao, Vader-Pohl et al., Taylor and McLennan, bottom line is the continental crust has between 7 and 8 terawatts of power. What does that mean? It has a very specific range of potassium, thorium, and uranium abundance. It's amazing, it's a really small range, but it's between 7 and 8 watts of power. Okay? If that's the case, and you say that the Earth has approximately 10 terawatts or so of power, then you can get down to scenarios where that's the range left in the mantle. So, for every geodynamicist and budding geodynamicist in this room, can you generate plate tectonics, mantle convection with negligible radioactive power? Because the continents have taken that away. Okay? So, I want you to pay attention to that. If you like my model, you might have, in my estimate, I'll end with that, 12 terawatts of radioactive power in the mantle. If you like the, quote, ensitite chondrite model, the consequence is there's only 1 to 2 terawatts of power in the mantle today. Okay? Or if you like the Turcotte and Schubert model, you have even more power in the radioactive power in the mantle. So, bottom line issue, okay, where's your power?
Just before you carry on, Brad Hacker was probably only about 150 yards.
Yeah, that's
a paper last year, in which he pointed out that you could have as low as between 5 and 6 terawatts.
Yep. Murakami could be right too. Yes, I know. Yeah, that was a flippant answer. That just basically said I'm aware of the paper and I'm not a big enthusiast of the model, but Dave Stevenson helped us to remember whatever I say now, some parts of it will definitely change in 10 years. The model that Brad Hacker has is really quite a good model in many ways. It's really talking about some of the dynamics that are going on in the subduction zone environment and what's actually happening on the bottom side of the lithosphere, both the lithospheric crust and the lithospheric mantle, and mass exchange right there. And I really must be attentive to that model, and it really does, quote, limit the model. But then again, for geodynamic space that could be parameterized, let's take that 5 terawatts of power in the continents, then it's 5 terawatts in the mantle, in Marc Javois' ensitite model, in that sense. Okay. That's a good point. And I'm working with Andre and Steve Dye, and we're looking at, let's talk about compositional layers or large structures in the mantle, and LLSVPs is just one. Let's fill them up with a different concentration of uranium than what we would call the source of mid-ocean ridge basalts. So then let's look at what would be the consequences. Let's say, is it going to be dynamically stable if it has large amounts of uranium and thorium or power, radioactive power? That's a question that I think we all should be working on. But at the same time, my buddy comes out here and says, but we could potentially, and we are actually actively engaged in trying to promote the idea of measuring the geoneutrino flux. There's electron antineutrinos being emitted during uranium and thorium decay during the beta steps of decay. And the measurements so far are really quite good, except that they're all on the continents, and actually subtracting the continental crust from that is really a challenge. All right, now we're getting into some just plain old definitional space. Okay. From a planetary perspective, not a nebula perspective, I'll use words like lithophile elements: calcium, aluminum, rare earths, potassium, thorium, uranium. Atmophile elements, I won't talk much about that. The previous CIDER meeting that was at KITP was about volatiles in the Earth. And when we talk about volatile elements in the Earth, Today, we're really talking about the hydrosphere, atmosphere, those volatiles. When we're talking about building of planets, there's a different family of what we call volatiles. And then the word siderophile, Greek sideros, means iron, nickel, phosphorus, osmium. So when you're really talking about, let's say, where is 90% of the phosphorus in the Earth? In the core. And the same would be true about 90% or thereabouts of nickel in the Earth is in the core. I remember I gave a talk like this down in South Africa at De Beers about 20 years ago, and there was an argument going on, is that a reservoir or is it a resource? And Dave basically then became a consultant as to how to get that resource out, right? So these are the classification of these elements, and those are important, the lithophile and siderophile. This is from Bill White's book on geochemistry, and I thought this was great. All right, now I won't ask Ed Garnero this because he's already had. Ed, pay attention now. Come on, don't do that. Oh, okay. Yes. I won't ask you this question. I'll ask somebody else. No. Which element is improperly labeled? Right, Beth Ann? What?
Neptunium.
Ed, where is Neptunium? Oh, okay, right here. NP, not NU. Yes, it's a Nussel. Yes, this is in deference to. There you go. But in fact, I did this because lithophile red, these are really, really lithophile. But you know, Rick Carlson was talking about there may be niobium in the core. So no matter how red, maybe you want to start thinking of this as a little bit pinkish, maybe. A bit more like the color that's used on molybdenum. So when I say a certain element is lithophile, I'm not going to tell you my secret, but I know how lithophile it is, okay? It's sort of like, I've been asked a lot of times by physicists, is there any uranium in the Earth's core? Do you know my answer? Yes. The partition coefficient between the silicate fraction of the Earth and the metal fraction of the Earth can be described in a chemical system. And if you think that the partitioning between the mantle and the core for uranium is 10 to the minus 9, well, there's something like 10 to the 16 kilograms of uranium in the Earth, so there is 10 to the 5 kilograms in the core, okay? So there is some uranium in the Earth, but as far as everything we're going to be able to see and measure and taste, smell, or neutrino detect, there's no uranium in the core, okay? So, but there is a little bit of siderophility, all lithophility to every element in the periodic table. Somebody was asking me about distilled water yesterday, and they thought it was pure. And no, I promised, there's the entire periodic table and everything. Okay, so there's at least one plutonium atom around for everybody, right? So I'm going to repeat a statement I made earlier. If you put potassium in the core, be prepared to explain sodium, rubidium, cesium, lithium. The periodic table is my thing that Ed was using the other day. All the PKIKPs. Seismologists know what those mean. Geochemists know what these mean. And some people will do the one-stop shopping trick. I can put that into the core. Well, I always think of how much rubidium is in the core. Okay? All right, now back to more classifications. So you'll see two things here. This is the nebular environment, and this is the planetary environment. So in terms of classification of elements, we have twofold classification. This is at least something you can go back to and look at. I'll use the words refractory, major components, moderately volatile, and volatile. Okay, so when we start talking about the word volatile, sometimes we'll just bin those two together. So for me, potassium's a volatile element, just like carbon, hydrogen, oxygen, and nitrogen. Noble gases are volatile, but so too is lead, sulfur, rubidium, gold. Gold's volatile? You bet it is. Cadmium, halides. Yeah, these are the volatile elements in the nebular environment because the temperature at which they condense out of a nebular gas phase at a certain hydrogen concentration is low compared to our reference state. Refractory. Calcium, aluminum, titanium, thorium, uranium, rhenium, osmium, tungsten, molybdenum. Yes, these are the refractory elements. Those are the ones that we say in the bulk planet are in chondritic ratios. Okay, so as a starting rule, we'll go back to that. Okay. And these, yes, let me just finish this sentence. These elements here, magnesium, iron, nickel, cobalt, silicon, they're actually in between, and they are not fixed by the chondritic story. Yes, Mark.
In the planetary environment, most of the oxygen is in the mantle.
Yes, I agree. It took me a while to sort of find where was oxygen on this. Wow. Yes, let me put that in perspective. I put oxygen here, and I should also put oxygen here. Or I can actually exclude that because the atmosphere is not important relative to the mass of the planet. Okay, so that Mark's point is, if I could, I'd move that over to here. And he's right. Okay. Does anybody know how much oxygen is in the mantle by mass? You can. It's about 45 weight percent, but you can just say half the mantle's mass is oxygen. Okay. And if you're talking about the number of atoms, you can actually approximate the composition of the Earth by oxygen.
Yeah, just think of it as a stack of oxygen atoms, and the other thing stuff would be...
The whole Earth, including iron. It really is dominated by oxygen atoms. Okay, so, yeah. So these are the reference temperatures that we often use. There are that many significant figures, but... Where are they coming from? That's an interesting question. A lot of it is actually, I love history of science, and it's really a historical perspective. Some people will know about the JANF tables, and the JANF tables were some of the tables that were being created during World War II, and JANF stands for the Joint Army, Navy, Air Force, Joint Army, Navy, Air Force thermodynamic database, basically. And what were they worried about? Why were they actually calculating the composition of the condensing phase from a nebular environment? They didn't give a hoot about it. But they didn't want their rocket, the nozzles at the back end of rockets to actually clog up. Okay? So in their high temperature gas environment, they needed to know what precipitated out when. So any of you petrologists, you might want to go and work for the Joint Army, Navy, Air Force. Oh, they're separate now. But that's important. To them, they had to do the thermodynamics of what will precipitate out from a high temperature, hydrogen-rich system. And that's where some of that data came from. Well, then it expanded, and a lot of silicate systems were added to this, and in the 60s and 70s, the meteoriticists started looking at what will be the phases condensing out of a solar nebula, and it was amazing how you could use the JANF tables to actually guide your whole principle. And then they started cooking up chondrites and then trying to evaporate them, and actually, amazing. What condenses out and what evaporates up follows a very similar sequence depending upon how much hydrogen you have in your surrounding atmosphere. So really, the reference frame for where these temperatures come from really comes from really studying gas dust systems. Okay. What? Both thermodynamic calculated data and experimental empirical observations. Yeah, they really do. That's important. Let me keep in mind. I will show you a diagram where my x-axis is depending upon that information set. And I never really know the uncertainty of the x-axis because when I do my models for the composition of the Earth, I know the y-axis uncertainty, but I don't know the x-axis uncertainty, which is really what condenses out when and where. Okay. Okay. This has been up long enough? Any questions? I get tired up here after a while. So I added this one slide in specifically. In fact, I used it at the last CIDER meeting. And just really you notice how I say group 18 elements, group 17, group 16, group 1? I use those names and nomenclature from the periodic table. So when I say alkali metals, group 1, to me, potassium is not a lone stranger. I think of all of these. And just to put it in perspective, when graduate students take my analytical instrumental course, I always hand them for the first full month, I hand them blank periodic tables and fill them in. And they go, what am I going to get for a grade on this? It's really important. It helps you just to do the measurements of chemistry, is to really know the entire periodic table and which elements are really related. Why? Because if I know the potassium content of a piece of steel that somebody gave me, and I go, wow, this got potassium in it, I can actually predict some of the other metals in there. Okay? So as just a pure chemist, I can actually do a lot of prediction based upon these things. So these are the volatile elements, so sometimes when a cosmic chemist talks about it. All right, so interstellar nebula, maybe a supernova ended up adding momentum and mass to an interstellar gas dust cloud. We get rotation and collapse of that cloud and formation of the planets. What we're left with is really the guidepost to really understanding the system. These are chondrites. This is a picture of a chondrite. This, I believe, is Allende. Rick Carlson showed something similar. Something like that white, amorphous, not circular-shaped thing would be a calcium-aluminum inclusion, something that essentially precipitated out first in the solar nebula. Some of these more round fragments are chondrules. But remember, it's a heterogeneous mixture of different components with different formation temperatures under different conditions. That's what we then go on to call the Earth, something like that. Here's the standard model. It doesn't matter if you're on the left or right side of the room. It doesn't matter if you're a geophysicist or a geochemist or even a cosmochemist or an astronomer. There is a standard planetary model, and these are the rules we use. Okay, so it's not just, oh, I thought this up on Thursday. Where are our constraints? Well, if you're on the Earth, you have both orbital and seismic constraints. But if you're trying to guess what the composition of Jupiter is, you really only have the orbital constraints. And what do I mean? You're looking at the body, but you don't have the benefit to actually measure all but a few parameters. So we use the coefficient of the moment of inertia to tell if it's a homogeneously compressed body or a core and a mantle system, right? So those are the kinds of orbital constraints you get. And then the seismic constraints, you get the actual depth to the core mantle boundary. We'd love to know exactly the depth to the core mantle boundary on Mars and Mercury, for that matter. Then the next piece of information sets that you work with are chondrites, which are primitive meteorites. And chondrites are specifically rocks that have an intimate mixture of metal phase, pure metallic alloys, I shouldn't say pure metallic alloys like iron, nickel, and silicates such as calcium, magnesium, aluminum, silica silicates. Okay, so they're undifferentiated. And then so too you use the composition of the photosphere. The solar photosphere, analogous to the ocean out there, that nice blue ocean out there. You look at the skin surface of the sun and you look at the absorption spectra. I'll show you that in a second. That gives you a big constraint. Why does that give you a constraint? As I was reminding, I'll ask the question. How big, if you do this for your day job, don't answer. How big is the sun in terms of mass compared to the Earth? Now give me an order of magnitude. See, anybody want to go for 10 to the 3? No. But, I've heard 10 to the 6 and more than that. It is 10 to the 6. You need 1 million Earths to the same size of the sun. How big is Jupiter compared to the Earth? 10 to the 3, okay? So it's important to keep all these perspectives. So why did I stop for a second and make that point? If you know the mass of the sun, you know the mass of the solar system. Forget the rest of the stuff. It's trivial. It's a waste, I mean, we got 1 ppm Earth, so it's a trace element, just to put it in perspective. And we would refer to Jupiter as a 1 part in 1,000, that's a trace element too. So really, it's within uncertainty we know the system because it's the composition of the sun. Okay, but then again, we're only actually talking about the surface of the sun. All right, refractory elements, I've defined them for you. They're in chondritic proportion. The calcium-aluminum ratio is 1. Here's where the beginning. See where I'd put it in big red underline? Model dependent. So the absolute abundance of uranium, and you see we're now varying by a factor of 3, is a big unknown. Magnesium, iron, silicon, and oxygen are non-refractory elements. You're allowed to guess, that means. Okay? All right. Now, the next quiz question. Let's see. Barbara. I needed a seismologist. Barbara, Forgive me, please. If we take this, and this element, how much mass of the Earth have we described? One significant figure will do. 90%. She's really spot on. It's 93%. Okay? Isn't that amazing? Isn't that amazing, though? This is important to me. We're just quibbling about details now, right? That's exactly why the job is difficult. Those four elements are model dependent at the biggest, capital M, and they represent almost the mass of the Earth. All right, now, next quiz question. Adam. 3 more elements and we'll go over 98%. 3 more elements. What are they, Adam? You misspelled university on your T-shirt.
Yeah, well, I guess they didn't teach me about that.
It's okay. What three elements plus these describe 98%? And if you get one of them, I'll move on. Calcium. All right. Calcium. CG. Excellent. Who wants to do the last one? No, not sulfur. Forget sulfur. It's not important. Nickel. Those 7 elements describe more than 98% of the Earth. Let's go home. All right, I'm finished. It's 12 o'clock. Jackie?
Sorry, this is not relevant to those concepts again. The quantitic proportion there. In this case, is the quantitic well defined or not? Because earlier you said a quantitic.
I'm going to give you a reference. Okay. Chemical gradients in the solar system, non-refractory elements, and model dependent. That means how much potassium's in the Earth, how much rubidium's in the Earth, etc. Okay? And so in my space, these are refractory elements, these are moderately volatile elements, and that's the story. If I can define those 3 elements, the story is done. Okay? That's in many ways. That even includes the magnesium silica story.
Bill?
Yes. Oh, you.
Points 3 and 7 don't exclude each other. That is the solar photosphere.
That's 3.
And chemical gradient in solar system.
They do.
In terms,
Oh, no, this is a planetary model. This is a recipe. You go into your kitchen and you begin cooking. This is a recipe. There's nothing exclusive. One doesn't exclude the other. Just remember, these are your rules by which you should stay. And pay attention, there's chemical gradients in the solar system. That's all that point 7 is saying. Yeah. So if you're going to, to put it in perspective, don't say the Earth is the same composition as the Sun. All right? You wouldn't do that, but I'd have to remind people of that. What's that? Oh, yeah, now I'm going to talk about meteorites. Okay? Oh, boy, it took me forever to get this kind of information set into my head. I'm not surprised that you people are really swirling in this morass of words. Okay, here's some attributes. What is a chondrite? It's an undifferentiated, it's got chondrules, mixtures of metals and silicates. It's the oldest material around. Okay? So that's an attribute. Taxonomy. We actually define chondrites as to what they're based on their redox state, the size of their chondrules, the degree of alteration. Oh, I left off the amount of matrix it has relative to chondrules, and the degree of metamorphism or alteration. That's why we have like CM2 or CV3 or CV4 or EH6. Oh my God, it will take you forever, but this is just a useful thing. Another very, 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 very useful thing. A century and a half ago, Europe was really looking at all the animals and more. But a century and a half ago, Europe was looking at all the animals, and Charles Darwin was trying to actually understand the origin of species, etc. And we were classifying animals. Giraffes may be different from horses and elephants, but how are they related to plants and insects? We're pretty close to that level in chondrites. Paul Warren's paper, not only did it have some very important things, but he spent a page and a half in EPSL talking about taxonomy. November of last year. We're revising our taxonomic scales on a yearly basis on chondrites. That tells you how much we don't know, okay? Yes, last year in EPSL, there was a taxonomy paper. So keep that in mind. And in fact, when I was growing up, it used, when Harold Urey was talking, there were just chondrites. When I was growing up, there was carbonaceous, ordinary, and anstatite chondrite. Now we have things like Rumeruti and Kangagari and it's not pretty. It will have to sort itself out. It will take time. Oxidized, mostly iron is iron oxide, less iron or more iron. Intermediate redox state, reduced state, new families. Okay. Then there are things called not chondrites. I couldn't use the word achondrite because that's actually a term used in the business. And what is an achondrite? Well, they could be a piece of mantle or a piece of crust, as opposed to an iron, which is just a form of metallic core. Or Razvan, you have to say that all over again.
So, the achondrites are metal and crust from what?
Planetary bodies that have differentiated. Very good question. So you had little planetesimals that differentiated, and they had metallic cores and rocky outsides, or creamy nougat centers, whatever. But you disrupt them, and they get delivered to the Earth. And so you have a basalt, and you go, wow, that was a differentiated planet. In fact, some of the words that Rick Carlson was using, I can't even, come on, eucrites, howardites, diogenites, angrites. Oh my God, there's lots of words. There's just, it's what taxonomists do.
Or ordinary chondrites in the common.
Next slide. Oh, wow. Oh, and by the way, when I said not chondrites and others, well, there are pieces of the moon, pieces of Mars. And, the second last slide, which I won't show you, has a taxonomy. It's fairly complicated, Stony ions, disrupted fragments of the core mantle boundary of planetesimals. Okay? And they're completely a disequilibrium assemblage. Completely. Matt?
I had a dumb question. Would it be possible for us to find terrestrial
Chondrites?
chondrites on Mars?
That's their question. Go for it.
They found iron meteorites.
They found 6 iron meteorites. Oh, that's a good point. You can think about it for a second, but I will what? No, he wants to know Earth rocks on Mars. Okay. Yeah. Okay, so the answer is yes. You can predict how, it might be rarer than hen's teeth, but you can predict that the bodies beyond the Earth may have fragments of the Earth. Okay. The one thing I want, somebody remind me, I'm old and senile. What was that last question I really liked, or the statement? What? Say it loudly. No. Oh, iron meteorites, right. So, if you don't know it, these little Scooby-Doo motorcycles that run around Mars, and for that 90-day experiment that's lasted for 10 years or something like that, you can go and Google it. You can check out and see if I'm right or wrong. But it has bumped into either 5 or 6 iron meteorites. Okay? Zero question about it. I'll tell you, that means there's 600 chondrites waiting for us. That will put it in perspective. Okay? I was at the Goldschmidt meeting a few weeks ago. I, for one, would love to see. I'm thrilled that the Indians, the Chinese, and the Japanese are planning to go to the moon. Why? Because I want to increase our meteorite collection. Because they've been collecting meteorites on the surface of the moon for billions of years. Could you imagine a rock on the surface that sat on the surface right near the ocean for 1 billion years? It doesn't look like the same rock today. I had a question over here.
In what the meteorites on Mars, the chondrites on Mars will be different from the ones on Earth, or just because of the position in the solar system?
That's a testable hypothesis. Okay, that basically says, are the chondrites on another planetary body, catcher's mitt, are they catching different material or not? I guess my bias right now is they should be catching about the same sort of thing, but a lot of we can actually track back to the asteroid belt where, if you are watching it fall and seeing it through space, where it came from, you can calculate where it should have come from originally, and we've got them tracked back sometimes. But yeah, I don't see why not.
Mars is the same preservation problem as the Earth, but there have been studies of sample return from other. That it would be a country.
It's like Vanna White. I show you this. This is the important part of this diagram. Okay. Now, So you can go on to the meteorite catalogs, but pay attention to this. Fall statistics. What does that mean? I saw something fall in the sky last night. Well, in fact, perhaps Louise Kellogg was at the cutting edge of this whole phenomena, but it wasn't too long ago. What was it, 4 months, 6 months?
It was in April.
April.
It was on the other side of the country, but it did happen in April.
Right. The only reason I knew to ask Louise about this is because it fell in the Sierras.
It fell, between basically, actually Berkeley science. Yeah, you should ask us.
Oh, no, I'm asking her, Barbara.
It went, a fireball went over and then exploded and fell into the Sierra.
Okay, so what happened was a bunch of pilots, that's a cool job. They actually get to see fireballs through the sky very frequently. And that's how we know sometimes. And there's lots of cameras that are just simply pointing up in deserts to watch things falling through the sky. But there was a meteorite fell, and it was in the news is highlighted as something about the size of a Volkswagen bus, I think it was the term. Refrigerator, okay. Come on, you're a geophysicist. It's the same order of magnitude. I can model a Volkswagen bus with a refrigerator. It's hollow in the inside, same density, right? But, they're falling all the time. So what happens basically is this. There's been about 1,100 meteorites fallen to the Earth that have been observed in the last 1,100 years, right? That doesn't mean that's how many fell. That's how many's been observed, right? So based upon a nice number, 1,000 data points, 80% of the stuff that's fallen to the Earth are ordinary chondrites. I'm sorry that the percentage sign's here, but if you add 9, 4, 2, and 80, you're down to maybe 6% iron and a few percent stony irons. But basically, iron meteorites, which are really beautiful to look at, really insignificant in terms of what falls to the Earth, chondrites. We're making all of this story up about enstatite chondrites. See how popular they are? 2%. 2% of all the things that have fallen. Interesting. I'd be careful making strong statements about enstatite chondrites, by the way. Yeah. No.
How do you age date the fall to the Earth?
How do you age date? There's two questions. The one, age date of fall to the Earth. Of course, you must not be talking about the age of the fall, because what you're talking about that fell last night. Oh, so this number is actually, where did I get this number? I just basically know from the literature. There are old. Let me start this sentence again. I remember I've disturbed a few people in the business. Oh, but we have chondrites that are many 100 million years old because they've been found in, not the KT boundary, but they've been found in the geological past, okay? But, when you're really talking about our repertoire of meteorites, it's what farmers have found in their field, and that used to be the big reservoir, but it's actually now, it's an entire industry to get on get your backpack on and go down to Antarctica and collect meteorites off the glaciers there, because and we have a little less than 10,000 meteorites in our collection. So basically, what?
16,000 Antarctica.
Okay, 16. I don't remember these numbers, but yeah. So here we are talking about very, very large numbers. Very, very few have been studied in the detail we would like them to be studied in detail. And really the one to me that tell the best story is what is the proportion of that coming down. Now, why do we actually get biased in this regard? Because for me, for instance, looking at the volatile element inventory is not messed up, because the ones that have been in Antarctica, they've been sitting in ice, they've gone through freeze and thaw, and they've gone through some differentiation process. The ones that are sitting in Antarctica, in the Sahara, also go through. The ones that are sitting in Western Australia also go through that. They're very, very, very useful, but you have to deconvolve part of the signal that is held within them. And that includes calcium and aluminum. Some of our chondrites really terrible calcium aluminum ratios. And so for us, I'll say the calcium-aluminum ratio is 1.1 plus or minus 0.1, but that's because I've already excluded what I would call the weathered or altered ones. But I've spent time talking to meteorologists, people who make it part of their industry. A bunch of people at UCLA, I know Rubin and Wasson, and these people have been studying these for a long time. So even some of the things we call chondrites have been compromised due to surface weathering phenomena.
So do you think that's representative of what the asteroid belt looks like, or do you think that's just a preservation factor of what survives?
Well, let's go with the assumption that this might be representative of what the asteroid belt is today, but the asteroid belt has all these gaps in it called the Kirkwood gaps, and it's been completely processed at some level. So it may be representative of what it is today. I don't know, but we also know that what it is today isn't what it was. Paps, and then...
There are strong barriers, depending on which of these families of meteorites is needed, actually crossing the atmosphere once more.
Well, you're introducing an interesting point. There are phenomena that are associated with crossing the atmosphere, too. Yeah.
All these faults are probably related to something called sporadic meteorites.
Sporadic?
Yeah.
Okay.
Do we have any geochemical constraints on the meteorite showers that we regularly observe? I mean, most of them probably come from the comets, but some of them are not. Do you know about their comets?
Somebody else has to answer that question.
I mean, most meteor showers associated with comet tails, passing through comet tails, and we have collected atmospheric particles from them. So there are interstellar dust grains associated with those meteor showers. And in terms of specifics, I can't say too much about it. I think they're mostly olivine and aggregate. But you're talking about things that you might know.
And you're talking about some of the collections that we had from the Brownlee types experiments? Yeah.
This is Brownlee.
Yeah.
You want to look it up.
Yeah. There's lots to study out there that keep coming towards us. Did I see a hand over there when I get over this side? Okay. Yeah, by the way, I'm about 1/3 of the way through. But I knew I had to go slow because there were a lot of questions I found. All right, so here is a 1950s article diagram. It's called the Urey-Craig diagram. And really, iron oxide divided by silica in a molar ratio. Okay, so iron oxide is not the iron tied up in the Earth's core. Okay, and then this is iron metal plus iron net sulfide, troilite, divided by the silica. So that's the iron tied up in the Earth's core, if you will. Okay. And so the yellow here, oxidized, are the carbonaceous chondrites, and it represents a field of the material. The green are the ordinary chondrites, and so 80% of them are sitting there, right? And then the enstatites, wow, they really don't have oxidized ions. They really sit right on the y-axis. And where does the Earth sit, and what is the size of the uncertainty of the Earth? It's smaller than the size of the star, just so you know. Okay? How do I know it that well? Well, in fact, one of the conclusions that I made in McDonough and Son was one ratio, and I'm really proud of it. The aluminum-iron ratio I felt very confident about, except until somebody from Bayreuth put aluminum into metal. But if you work with all of the aluminum in the planet is in the silicate sphere of the Earth, then what you have is a constraint. That is a fraction of refractory elements. And so the iron-aluminum ratio is constrained to within plus or minus about 10 to 15%. And in fact, that's why I said 10% iron uncertainty, 10% aluminum uncertainty. But the iron-aluminum ratio is constrained, and that tells you how much iron and aluminum is in the system. And that doesn't matter if you like Murakami's lower mantle or my lower mantle. It's not a big uncertainty in that regard. And that puts it right there. 10 minutes, yeah. I know 12:30. I will stop at 12:30. Okay, so... Oh, it is? Okay. Intentionally. So... I will get through what I get through. That's it. I'm not going to rush it. So the iron content... the Earth looks like an azotype chondrite, right? Okay, I'll make that argument easily. Oh, this is the absorption spectra. So when there's a little gap in the hole here, that means that there's a lot of that element in the sun's photosphere. So this is the absorption spectra of the sun. This is the near infrared. There's 50 lines here. This is the ultraviolet. As you go from the ultraviolet to the infrared, you can make a quantitative measurement for atoms in the sun. And then you can plot the log abundance of elements in the solar photosphere and the log abundance of elements in a C1 chondrite. And what's amazing is noble gas, noble gas, noble gas, noble gas, noble gas, hydrogen, carbon, oxygen, nitrogen, lithium, everything else, periodic table on the line. Okay? So, in fact, I feel pretty good that the composition of the Earth can be approximated by the composition of the solar photosphere. Better yet, this is not a C1 chondrite. It's actually an ugly rock to take a photo of. But chondrites are, without question in my mind, a guide to what has to be a planetary composition. So you remember I said how to build a planet? Oh, let me see if I can quickly go back there. Oh, this line right here, chondrites are key, and so too is the photosphere. That's the reason why. This line right here, the mass of the solar system is the mass of the sun, and I can take, oh, by the way, there's only 5 kilograms of C1. There's 5 different types of C1 meteorites, and there's 5 kilograms all total. We're making this whole argument on 5 kilograms of rock. What? Oh, they on this log-log scale, they just pull up a little bit more scatter. Yeah, it's a huge scale.
So what's wrong with NCNO on one hand, or NMC, and then lithium on the other hand?
This is due to burning in sun. This is being consumed in the sun. Lithium is. It's lithium mass 6, mass 7. It's really, yeah. Nuclear fusion burning processes, that kind of stuff. And yeah, the C1 chondrite is very... Oh, we won't make the Earth out of C1 chondrite, or we would have 5% or so mass sulfur and water and CO2.
So what about the nitrogen and the carbon?
What about it? It's nice.
I mean, they are not on that line either, so why is that?
Oh, these are the truly volatile elements. And remember the question you had about snowline that we were talking about? So the outer gaseous planets have lots of those elements. The inner gaseous planets have a lot less. And the chondrites here do have fractionation of those volatile elements from the sun's composition. And remember, the sun composition for the hydrogen-helium ratio is there's compositional heterogeneities inside the sun, by the way. The core of the sun is consuming hydrogen and making helium. And there's a large amount of, there's a big change in the hydrogen-helium ratio as you go down in the sun.
Would it include the CI chondrite condensed from the solar nebula?
No, I would have constructed that sentence by saying that a C1 chondrite has sampled, on average, the material available in the nebula. That's how I would. The other one imposes too much process. All right. In this amount of time, I will get through this next concept. All right. Everybody in this room will have heard of Forsterite or Olivine, Mg2SiO4, and everybody should have heard of the mineral enstatite MgSiO3. The fundamental point to be taken away is this has 2 atoms of magnesium to 1 atom of silica. This has 1 and 1. Okay? Now, if you want to take my model, or you're going to take Don Anderson's model, or you're going to take Murakami's model, or a lot of other models, the fundamental phenomena that's being discussed today is the ratio of olivine to enstatite, magnesium silica ratio of 2 to a magnesium silica ratio of 1. All right? Okay. That's it, really. So, how much olivine did we accrete? Remember I had a question 2 days ago. I want to know exactly how much olivine is in the top 600 kilometers of the Earth. This is why I want to know. Now, I think that when people subscribe to, quote, an enstatite chondrite model, they're being too rigid about the definition of what are the potentials for enstatite chondrite models. There's another field called astromineralogy, where they're collecting absorption spectra on interstellar gas dust clouds. They're looking at accreting nebulas. They're looking all over to see what is the mineralogy already out there. Okay. Now, if you look at the interstellar gas dust clouds, you will see that some of those minerals are almost useless. I mean, they've really suffered radiation damage extraordinaire. But one of the things, This was a study where the inner portion of the disk and the total disk was looked at. So this is outer disk and inner disk. There's been several of these measurements, and what they find is that the inner disk, in some of them, are olivine rich, and the outer disks have a mixture of olivine and pyroxene, and the spectra aren't very pretty. But the other thing that they found is that the inner nebula regions are tending towards highly crystallized. By the way, for an astronomer, highly crystallized means about 2% crystallized. Okay? Okay, so that word highly needed to be placed in context. But nonetheless, to me, what do I take? I take this as, one, you clearly would assume across a disk there's a temperature gradient. Okay? Secondly, the previous diagram, I was emphasizing that olivine is a higher temperature phase than anstatite in a condensing nebula sequence. So you would predict that the olivine would come out first. Olivine would be dominant in the higher temperature regions, and olivine and pyroxene might be occurring in the lower temperature regions. My argument would go, you might intuit that the Earth could be an olivine-rich anstatite chondrite. Note that word, olivine-rich anstatite chondrite. Okay? Or to turn around, the olivine to pyroxene proportion in silicate bodies is not fixed, and how it got there might be due to these kinds of processes. Patrick? The uncertainty is considerable. I mean, what you can see there is a couple of different, waveforms coming in. There's lots of uncertainty. In fact, this is looks like this. What I'm doing is, one, I'm promoting this field of study, and I'm promoting discussions that go on between astronomers and earth scientists. We're actually beginning to measure beginning to define the presence of exoplanets and also define the spectral variation of exoplanets. But we can also do mineralogy in space. We can definitely tell silicates. We can definitely tell silicates from sulfides and metals. And additionally, we can actually, they've imaged quartz in space. I don't know which form of the polymorph, but they've measured it. So this is not high precision work. But this is seeing differences between inner and outer portions of disks. How could we interpret that? Okay, so this is not 1 sigma work. This is work in progress. And I think, to me, it makes sense to think of the magnesium-silica ratio as this story. And I'm going to leave it there. The proportion of olivine to pyroxene in an accreting body. And there is no hard and fast rules. Just think of it as a guiding principle, and let us try and figure out how much olivine to pyroxene there is in the silicate Earth. All right, I didn't get through it all. That's it.
We have 2 minutes for questions.
I have 17 slides if you'd like. Steve.
What's the magnesium-silicate ratio of the Earth?
Oh, okay. You're going to make me do this. I know you are. Yeah. So Steve said, what is this value here, magnesium to silica, for the silicate Earth? So in fact, these green dots here are the anstatite chondrite value. The blue is the ordinary chondrite value, and the red is the carbonaceous chondrite value. Now, I don't enjoy provoking Marc Javois, but from his literature, those are his estimates. Not
all over the place.
Oh, I didn't say that, Dave. Don't say it again. Steve, what would you like it to be? Okay, this is an important takeaway message. Does everybody understand why I get prickly when people said I used a magnesium-silica ratio of chondrite?
What's the magnesium-silicon ratio of the sun?
Oh, that's a great question. It's right there.
Yeah.
It's right there.
Yeah.
That's C1 chondrite, by the way.
Yeah.
Okay, that's a great question.
Plus or minus 25% uncertainty.
Yeah.
Oh, it's not.
That's a big error.
Yeah, okay, but it's really only up to about there, down to about there, over to about there, over to about there. So, make that, 25%. It's not down here. Come on, let's keep it. You know, why did we get this variation? I think it's simply due to I haven't even told you about high ion, low ion, but I think it's really due to the pyroxene to olivine mixtures in systems. Now, the pyroxene olivine mixtures is not the same as the refractory element budget. Somebody back there was having a hand up. Jackie.
How come this ratio is below 1? I thought the upper mantle has, mainly olivine.
It's a kilogram. It's not mole to mole.
Oh, okay, it's not. Why do you do that?
Yeah, this is a great question. I do not want to skip over this question. I wrote in Rick Carlson's book on the treatise of geochemistry. I wrote a chapter on the composition of the Earth's core. In fact, probably most of the geochemists in this room do not know that. I mean, the reason is because this is important to mineral physicists. And in fact, when I asked some friends to review it in mineral physics, they go, I need to know this in atomic proportions. And so, in fact, in my chapter, I actually have both, because a geochemist thinks in grams per gram, or kilograms per kilogram. Weight percent is what's the unit of our day. And so sometimes, regrettable, I will do it in gram per gram basis, and sometimes I will do it on an atom per atom basis. And really, when I want to confuse Jackie, I'll switch my scale. Sorry, Jackie. Oh. Matt?
So, Bill, if this were truly mixing between the carbonaceous stem member, olivine rich, and andesite stem member, it should be a straight line in this plot. The silica is the denominator.
Okay. Right. Okay, so let me just review for you. You can mix this way. You can mix this way. You might be able to mix between this one and this one. But remember, these are the average compositions. I have not given you the cloud. Okay? Just. And I wouldn't say it's like that. Remember, this is a flexible parameter, and this is a refractory versus a flexible parameter. All right? So it's just, just don't think of it as mixing in that sense. Beth Ann had her hand up.
I was going to ask that. So the idea that the variations in magnesium silica ratio in different chondrite types, the idea that that's due to picking up varying amounts of olivine or pyroxene in the nebula, would you also expect to see other variations in the more to less volatile elements correlated with that? If that's truly where the ratio comes from, and do we in fact see those correlations? If you're sampling different parts of the nebula, different rates.
Okay, so let me try and repeat that. But basically, in trying to do these predictive models, you've got a couple of parameters. One is, what is the relative mixing between olivine and pyroxene? And in that sense, that sets the magnesium silica ratio. And then I switched to this for some reason. I'll show it to you in a second. And then the x-axis was refractory element aluminum relative to silica. So if you had lots of N-state. Well, there's essentially two families of materials. And one way to think of it is, on Thursday, I'm going to establish my olivine to pyroxene mixture before I make that portion of the cake. And either on Wednesday or Friday, I'm going to add in how many refractory elements. And in fact, I've heard people say, well, how much chondrules or how much CAIs represents the Earth, calcium aluminum inclusions, or the high temperature component. So the way I think of it is, on that previous diagram, in contrast to Matt not trying to make a hyperbolic thing, the variation in this axis tells me how much refractory elements I have to the major element components. And the variation in this axis tells me how much pyroxene to olivine I had in the system. So there's a lot of free space, and there are no highways. So you're allowed to travel anywhere you want in this thing. All right. If you notice one thing about the previous diagram, you'll see it here too. Now, again, as we started off, 4 elements make up the Earth: magnesium, silica, iron, and oxygen. So this actually ternary chemical space is projected from oxygen. Oxygen's looking down and says, where do I sit on the triangle iron, silica, magnesium? Smack in the middle. And the one point I really want to make up here, so there, 93, 98, the Earth doesn't sit within the field called chondrites. My Earth sits outside the compositional space of the chondrites. There's the difference. I let chondrites be a guide, but I do not, it's like marriage. You can't tell me what to do. Thank you.